Hello guys and welcome back. In this video I wanted to cover a few math functions that we're going to be using throughout this workshop. We may not use them all this week, but hopefully we will, and you guys will find some use to them. So the first one that I want to talk about is the sine and cosine. And what this does is, given any input value that goes from 0 to infinity, it's going to always return a value that goes between 0 and between 1 and minus 1. The sine function starts at 0. The cosine function starts at 1. So there is an offset between these two guys. Now, well, how do we make use of this in CG really depends on the situation. I don't have a perfect example to this right away, but we can use it anytime we want to make a value that goes from 0 to x value and make it repeatable into something that we can manage. And I want to show how to do this and what we can create from it. So I'm going to create a line, and I'm going to have it aim at the z-axis, and let's give it 100 points. Okay, so now we have 100 points, and they're going from 0 to, let's see, let me unpin this. They're going from 0 to 1. I want to increase that, so let's have it go from 0 to 100. Okay, and I'm going to create an attribute wrangle, and I want to override the height, the y position of these guys. So I'm going to say v at p dot y is equal the sine, and I want the sine function to use the point position, which is the p dot z, and that value starts 0 and ends 100 here, and we're going to pass that to the sine function and see what it gives us. So I want to override the p dot y by the v p dot z. Okay, and you can see it give us back this this curve. Well, we can divide this by 10, for example, and that will make the curve smoother. It will give us less repetition. Okay, we can divide it by 4. We can multiply this by a value, let's say 5, and now the curve is higher. Now I'm going to copy this, and I'm going to show you the cosine function. Same thing. Cos is the function, and let's merge them together. And you can see that one starts at 0 and the other starts at 1. And again, hopefully we'll have an example on how to use this, but this is the sine and cosine. You give it any input, any value, and it gives you back a value between minus 1 and 1. The next function I wanted to talk about is the dot product. And let's say we have a sphere here. Okay, and I'm going to compute the normal on these points. Let's put down a facet node. Let's compute a normal, and see the normal is pointing outward. And I'm going to create a point like we did before. And let's copy these actually. So I'm going to create a point, and let's place it. Control middle click to zero out any attribute. Let's move the point, and now we have the vector. Cool. And I don't want this vector. What I want to do, I want this vector, but I don't want to override n. So let me delete all this except the goal. And what I want to do is I want to compute something called the dot product between the vector that is equal to the point position subtracted by this, so the vector that goes from this point to this point, and the normal. Okay, so let's do that. Let's call this vector, this is goal position, and let's call this goal vector, let's call this target. Okay, so it's from here all the way to this point, and we may have to invert it. It's equal to the goal position minus the v at p, and we can plug it into n to visualize it briefly. Goal position, cool. So it's, and this is the vector, And to comment out a line, we use this double slash here, and that will remove this from being executed. It's like writing comments. It doesn't do anything. Okay, so I want to compute the dot product between this the normals and that vector that we just saw. So, and I'm gonna add this as a float. The result is a float. So product result is equal a dot function between the target and the v at p. V at n. We want to compute the dot product between the normal and the vector that is the distance or the needed to move this point from here to here. And let's take a look at the values. It's going to be hard to see the values, but what's going to happen is the dot product takes in two vectors, and if they are parallel to each other, it's going to return 1. If they are apart from each other, if they are facing away, it's going to return -1. And if they're 90-degree apart, it's going to give you back 1. So I want to visualize this result. And the reason it's like this right now, it's higher than 1 and -1, is because the vector is not normalized. By default, the normal is always normalized, and what that means is the length of this vector is always equal to 1. But in some instances, like the vector that we're constructing from here to here, it's not normalized, so we need to do that. So I'm going to use a function called normalize to normalize the vector. So I need to normalize this, and that will not change the direction, it will change the magnitude, so it's always equal to 1. And I'm also going to normalize the normals to make sure that it's correct. And now the dot product, you see it's between -1 and 1. And it's 1 where the point are facing this point, and it's away, it's -1 when the points are facing the other direction. So let's plug this into the color and see how that looks like. F dot product. And let's see. This. Dot product, sorry. Yeah. So you can see now that's the result. And when the point is, think of this as a point light. Okay. Imagine this is a point light. When the surface is hit with this light, it gets illuminated. When it's not, it doesn't get illuminated. And that's how it works. And this is how the Lambertian or the diffuse shader compute whether a light is facing it or not, whether a light contributes to its illumination or not. And this is done using the dot product function. And what we can do is we can use this in many ways to find whether two vectors are facing each other or not. For example, let's say I have a sphere and it's animated, it's going upward. Okay, so let's say $F, and I'm going to compute the sine of $F, which makes it go up and down. Okay, let's multiply this by 10, so it goes higher. So now the point is going up, and then at some point it's going to start going down. Let me multiply the frame by 2 or 3 so it happens faster. Okay, it's going up and then it's going down. Cool. Now what I'm going to do is I'm going to use a node called trail that we used last week to compute the velocity. And what the velocity vector will do as the point moves. Let me change this to a sphere. Let's add more points. You can see the velocity vector, how it's pointing this way. And then as the sphere, see that 0, and then as it starts going downward, it flips, the velocity vector changes. And we can use a vector that is pointing in the up direction, so it's equal 0, 1, 0, and then compute the dot product between the velocity and this guy. So let's do this. Let's call this let's plug it into CD directly. Or no, let's, yeah. Dot product is equal to the velocity, v at v, and the velocity vector, that's its name. You see it here. And I want to compute the dot between the v at v, and let's normalize it because the magnitude doesn't matter at this point. And I want to compute that with an up vector, and it's pointing, it's 1 in the y-axis, so the vector is pointing upward. And let's connect this and view it as the color. So v at CD is equal 1. So it's white now. Let's hit play. And sorry, that. Okay, let's turn this off. Let's play. It's white at the beginning and 0 when it comes back. It's gonna, yeah, it's white when it's going upward and 0 when it goes down. Up when it goes up. When it's aligned with the same vector. And let me turn this origin node. Yeah. So this is the y axis here, and these two are 0, so we have a vector pointing upward. And then when the velocity is aligned with this, it gives us back a value of 1, and when it's not, it gives us back a value of black. So what we can do with this is, let's say we have particles that are going, debris for example, or a splash that is going upward, and then we want to, let's say we have a debris and we copied multiple rocks to those particles, and we want them to rotate really fast as they go up, and then slow down or lose their velocity when they start going down, lose the rotation. We can use this guy to drive that. We know when the particle is going upward and when it's going downward. So this is one way of knowing that. Cool. So the next thing I want to talk about, this is the dot product idea. The next thing I want to talk about is the cross product. And the dot product requires two vectors, and it gives us back a float value. This cross product thing requires two vectors, but it's going to give us back one vector. And this is my input A, and this is the second vector B, and this is the resulting cross product vector result. And what it does, it takes these two guys, it constructs a virtual plane between them, creates an orthogonal vector at the center of the surface, and then places it at the intersection or the beginning of these two vectors. And that is the cross product of something. So let's take a look at this. This is very, very powerful. I'm going to use it in this week. So I'm going to take the normals as well. Let's compute the normals. And all I want to do is I want to take the normals and compute the cross product of the normal vector with an up vector. Let me set this to polygonal mesh and just have few faces. That's it. And let's create a wrangle node. And I'm going to override the normal with this resulting vector. So v at n is equal the cross between the normalized normal, v at n, and an up vector. So 0, 1, 0. And let's end this line. And you can see now the vector has rotated and changed its orientation. Let me increase this so we can see it better. So we started with this. This is the vector here. We gave it an up vector, which is here, pointing this way. And let me visualize the up vector for you guys. So an up vector is equal to that. Okay, so this is the up vector. And this is the normal. Okay, and the result between these two guys is going to create a virtual plane. Let me reduce the number of points so we can see it better. it's gonna create a virtual plane between these two guys, which is like this, and then compute the orthogonal vector to that plane, and then place it here. And this is the result that we get. That's the vector that we want. And this is very useful to create a vector that follows the curvature of the mesh. And you can already see that. Let me create the toy geometry, and we're going to take the normals, and let's run the same thing. Let's make sure it has normals, and let's visualize that. And let me set this back to 0.1. And this is the original normal of the toy geometry, and then with the cross product you can see how it's following the curvature of the mesh. We can also compute another cross product to inverse this vector, but we'll do this later, to create change the orientation so it's facing this way or this way to get more interesting directions that we can use later. So I think that's pretty much it for the math function. If I remember something, we need something else, we'll talk about it. But primarily the sine and cosine, and then the dot product and the cosine, the cross product. So I've done all this using coding, which is pretty simple. But I want to show doing the same thing using point VOPs. Point VOPs are the same as VEX in terms of performance. There is no difference. It's just which one are you more comfortable with. You want to write code, you can use the Wrangle node, or you want to use an interface and connect nodes and things like that, you can totally do that. So let's take a look at a couple of examples that we did. Maybe this sine. Yeah, so let's do this again. So I'm going to copy the line, and I'm going to create a point VOP. I'm going to connect this here. Okay, let's dive inside. We have the P, this is the position, and to access its component we need to use a vector to float, which splits where we can access the X, Y, and Z individually. And I want to take the Z component and compute a sine function for that. Okay, and then we want to override the height with this result, but keep the Z and X the same. So we need a float to vector node to reconstruct the vector. I'm going to plug in this result into the Y component, leave the Z as it is, and leave the X as it is. And then we're going to plug this into the Y position. You can see we've got the same result. We did the multiplication. We divided the P.Z by 4 and multiplied it by 5. So let's do that. Let's add a multiply by a constant, and let's multiply the Z position by 4, and divide the height by 4. So divide constant by 4, and let's increase the height by 5. Multiply constant, and this by 5. And this is exactly what we did here. You can see it's the same result. For the cosine, let's copy this, dive inside, and just swap this with a cosine function. Okay, now we have the cosine, which is equal to this. So here, I have a couple of nodes, and this one is just a couple of lines, or one single line to do that. So it's up to you, whichever you want, you're comfortable with. I want to show this example because I think we may want to do it in point VOPs rather than Wrangle. So I'm going to connect the first input and the second input. And what we did, we computed a vector that is the vector needed to move the points to the goal. So let's do that. But first we need to import the second point value. And to do that, I'm going to use an import point attribute. Okay, and the point number is equal to 0. And I'm going to create a constant, and it's an integer, and its value is equal to 0. Connect that. For the file, I'm going to connect the second input because that's where it's coming from. And now if I set this, you can see all the points are overwritten and moved to that position, but I don't want that. This is just for verification. I'm going to compute the vector that starts from here and goes all the way to position, and let's take a look at that and view it as the normal. Let's see, that's the vector, and again we change the viewport back, so that's why the length there, and then we can compute the length of this vector and plug it into the color, and now it's super bright, so we need to fit this, and to do the fitting we're going to use a fit range node. I'm going to say the range is between 0 to 15, and we want to flip it. Instead of black where it's where it's close, we want to make it white, and then black when it's far away, when it's not facing. So let's do this, and as the object gets closer, we're getting this fake illumination effect, but this is different from the dot product result. We can also do the dot product if we want by, let's copy this and let's compute the vectors and the normals, and we want to compute the dot product between the normal and this vector. So dot product between that and this, and we want to normalize them first. So normalize this and this. Let's connect this result, and now we have the dot product result with the point. Cool. So this is the implementation in PointVop. Let's do the cross product, and we've covered everything. So let's copy this, and this is our normal original. Let's set this to 0.1. I'm going to create a PointVop. Let's dive inside, do a cross product between n and an up vector, which is set here. So let's connect this to n, and now we have that. We can also do another cross product, so I'm going to copy this, and I want to compute the cross product of this result with the normal again and plug this in. See how it's facing upward now? Okay, and we can use a mixed node to mix between the two. See how it's doing that, rotating between the two. And we can use any noise maps. So noise is basically similar to the sine or cosine function. Actually, the Perlin noise is based off sine and cosine. A noise function behaves the same way. It gives you back a value that goes from -1 to 1 or from 0 to 1. And this is the result. The cool thing is you can change the frequency. It's different, not like the random function. It has a scale, so you can increase the amount of noise or not. And I can plug this into the interpolation bias here and take a look at the normal, and now it's being driven by this map. So I can add noise here, and it's mixing simply between the two vectors. Cool, so that's the PointVop, and hopefully this is all we are going to need for this week. Thank you guys for watching, and see you in a bit.